Good evening, everybody. My name is Wayne Ranney, and I serve on the board of directors for the Grand Canyon Historical Society. And we welcome you to tonight's virtual outing. The Grand Canyon Historical Society, our mission is to celebrate and promote the study and preservation of the Grand Canyon region's cultural and natural history for the education and enjoyment of its members and the public. And just last year in 2024, we celebrated 40 years of existence when the society was started by some pioneer members of Grand Canyon Village. We encourage you to become a member. Our dues are only $35 a year. We are an all-volunteer organization, and we're hopeful that many of you can join us so that we can continue to expand all of our activities like these virtual outings and in-person outings and our tri-annual history symposiums. If you do become a member, you'll get 4 issues in the calendar year of the Old Pioneer magazine, which has a lot of history articles about the Grand Canyon and the Grand Canyon region. So we do these virtual outings. We conduct tours at the South and North Rim, and you can find it on our website. Our website is very easy, grandcanyonhistory.org.
Tonight, we are so fortunate to have Laura Crossey and Karlstrom present Grand Canyon's spring and groundwater geoheritage. We just don't get any more lucky than this. I'd like to introduce these two amazing people with a little joke to start. These people are quite a pair of docs. And that's a paradox, and that's the paradox formation. And so that's a little joke there, sorry. Both Dr. Laura Crossey and Dr. Karl Karlstrom teach at the University of New Mexico. Laura specializing in low temperature geochemistry, including diagenesis, hydrochemistry, and geomicrobiology, while Karl specializes in structural geology, tectonics, and landscape evolution. Together, they've worked on Grand Canyon's Trail of Time exhibition, not just working on it, but creating it and seeing it through using $2.3 million from the National Science Foundation. Laura's research contributions to Grand Canyon are amazing, and her contributions specifically to Grand Canyon geology include documenting mantle degassing in Grand Canyon springs, using noble gas analysis, quantifying mixing of lower world and upper world components of Grand Canyon aquifers, and monitoring inner canyon springs to establish a baseline for water supply and water quality. Not to be outdone in this paradox is Karl's Grand Canyon research, which focuses on tectonic history and ages of the Vishnu basement and supergroup rocks. Along with the quaternary evolution of Grand Canyon landscapes, including incision history, get this, resolution of the 140-year-long age of Grand Canyon debate via the Paleo Canyon solution. Redefinition of the Tonto group and its marine transgressions. Did the Tonto group really do transgressions? I dread to think. And fault-related flow paths for Grand Canyon groundwater. It just doesn't get any better than this. With that, I am going to stop my screen share, and I'm going to ask Karl and Laura to start theirs. The first question of Laura and Karl, I will ask you, may we record this presentation you're giving tonight?
Yes, you may.
You may.
Thank you so very, very much. You're on your way.
Okay. Thank you for that introduction. We're going to go back and forth, and I think we'll see how it works. But why don't you start off?
Yeah, if we have any click and clack fans out there, you might kind of catch on to the idea. And Tom, you didn't mention that Karl and I are married also, so it makes fieldwork a lot more convenient. And
I didn't see that in your bio. I'm sorry.
no,
I won't make that mistake again.
that's okay. that whole name thing. But yeah, we're so happy to be here, and thank you. And actually, Haley was one of the ones that reached out about this invitation, and we couldn't have had a better day. And I'll kind of remind you why in a minute to do this virtual outing. But I just want to mention, because I know, Tom, you're preserving this, we really want to honor that, everybody, especially geologists, are standing on the shoulders of giants. And from a hydrologic perspectives, Peter Huntoon is a name that I definitely want to put out there as somebody who's done so much work on Grand Canyon, both mapping, structure, and hydrology, that it's pretty amazing. And then Abe and his team at NAU has been just grinding away with so many aspects of the springs. Mark Persone, who's maybe not as much known in the Grand Canyon community, is now at New Mexico Tech, but he's a fantastic groundwater modeler. And I'll tell you that there's not a very, there's not a tougher job in the world than trying to run groundwater models, which rests on the geology and the hydrology and the geochemical constraints and so forth. Ben Tobin, who's now in Kentucky, was the NPS hydrologist, and he's been fantastic. Larry Stevens and Jerry Ledbetter, many of you know them from the Spring Stewardship Institute. Hannah, now the park has made a fabulous choice, and Hannah's there with the resource division working on hydrology, and we're just going to see more and more terrific stuff going on with Hannah. So before we get too far down the road, I want to put in here a land acknowledgement. This is drawn largely from the NPS acknowledgement, but it recognizes that the Grand Canyon shares boundaries with many 11 federally recognized tribes who have used this area as their traditional land. And we acknowledge these people. We've been privileged to work on these lands within a national park and on these traditional homelands. So we just want to mention that, and of course always finish with the concept of the vibrant Native communities who are still here and contributing. And today, as I mentioned, is just a terrific day that we could have to give this talk, which has quite a bearing on groundwater and what are the threats to groundwater. And today we've got this designation of this fabulous new monument. Not new, I mean, many people have been working on it for a long time. But I'm just going to call it the BNIK, Grand Canyon National Monument designated, because I haven't heard any people talking about what it means. But down in the lower left, the term of this new monument, where the tribes roam, reflecting Havasupai engagement and the footprints for the Hopi tribe. And Navajo Nation, of course, is very central to all of this. But I'm highlighting in red here that that as wonderful as this designation is, we can't erase history, can we? We can't burn the book and not have the reality of the scientific effect and the real effect that some of our anthropogenic activities have had on things like the groundwater. So existing mining claims will not be affected by this designation. And so we're going to kind of dig into the weeds. We're going to take you into the weeds. And
it's pertinent to look at the Grand Canyon region because, of course, groundwater doesn't know about boundaries. Groundwater moves below tribal lands and park lands and community lands. And that's kind of what we want to talk about. But just to mention this term geoheritage that's in our title, to me, there's a kind of a seamless transition between human history, human heritage, which this society is about, and the earth and the geologic history that supports all this human. So this term geoheritage is really catching on in terms of the International Union of Geological Sciences. And Lori and I nominated Grand Canyon and the Great Unconformity as two of the first 100 geoheritage sites. And this was, we went to Spain to accept the dedication of these as two of the first 100. And look at these Zumaya, Spain turbidites standing on end, kind of reminds you of the Vishnu schist. But what a great place to think about geoheritage. In this part of the world, the indigenous people are the Basques, and they've been there a long time. But so this sort of the issue of how to honor indigenous backgrounds is everywhere. And so here's geoheritage, common geologic history. Now, I don't know if it's an expansion into deep time, but there's sort of three parts to this talk, and it builds on this thing that's tilted there is a field forum booklet we put together for a 2022 trip where we had Peter Huntoon and Ben Tobin, a bunch of experts, students. The idea is you get groups together to discuss the science, where we are right now in understanding Grand Canyon springs, groundwater, and travertines, and you get discussions, and it sort of motivates sort of next generation of students to keep going. So in this talk, we're going to talk building on that field forum and ideas from the paper we just finished about hydrotectonics. We'll talk about that a little more. We're going to talk about the Trans-Canyon Pipeline, the history of that, super interesting. Vasey's and Paradise, which we saw the pictures of, and in the end come around to the idea that maybe we're inducing seismicity below the south rim from pipeline water. So it's we'll cover a lot of stuff. It bridges history and geology.
So we're going to try to reach across bridge the gap for people that haven't been really as immersed in hydrology and hydrochemistry, but we're going to bring along a little chemistry from Albuquerque. It's the Breaking Bad kind of terrain. It's chemistry in the woodshed sort of thing. So you're going to hear some geochemistry, but it's not that bad. So we're going to think about three types of waters, and you all recognize the one on the right. That's the drinking water. That's good stuff. And then as we move to the left, we have, sort of not so good, even though, of course, Gatorade is a good thing to drink to replenish your what? I know you're all muted, so you can't really say it.
Electrolytes.
Electrolytes is what you want to be saying. So there's salts. There's salts in groundwater. And the saltier it gets, of course, there's a guideline as to how salty it gets. And that guideline for potable water that you're going to drink in your kitchen versus what you can perhaps feed to cattle and so forth. It's a little bit of a gray line, but we're talking about something like hundreds of parts per million of salt. So mostly water with a little salt. A lot of times we express that in quantitative terms, literally in milligrams per liter. So if you look at that bottle on the right, which is a liter drinking water, bottle, and picture an aspirin tablet, which is typically somewhere from 100, or if you're really having a bad headache, maybe you'd get a 200 milligram tablet. But we're talking about milligrams per liter would be like putting one aspirin tablet into the liter of water. So that's kind of an idea. Now, a Gatorade is more like almost a seawater kind of salinity, which is much saltier than what's allowed for potable drinking water. Seawater is about 35 parts per thousand. So that's 350,000 parts per million. So there's more like grams of salt in seawater. Okay, so that's not so good for drinking if that's the only water you can drink. All right. And then we go further to the left and we see a different type of water. What's in that can? And some of you might be familiar with drinking a can of things like that. It actually does have, sugar is a salt from a point of view of a hydrologist. So it has a fair amount of saltiness in it, but it has something else. It's got something in it that the other two don't have much of. And if I was giving this talk in person, I would be holding that can and I would be shaking the bejesus out of it. Okay. And if you were in the front row, you might start to get nervous because maybe Tom Martin has told you some stories about Laura Crossey. I mean, really, how crazy is she? And so if I pop that thing open, it's going to explode. The amount of power in even a small can of carbonated water is pretty powerful. So that's got CO2 in it. So we're thinking of three types of waters: pure rainfall, snowmelt, recharge, very low total dissolved solids. Then we get a salty water. How does the salt get into the water? It interacts with the medium of the aquifer. It leaches salts out of the rock materials that it's coming into. So that is the second water. And the third one is we're adding something to it. We're adding CO2.
Yes.
How we're doing it, that is a fascinating story into itself. So 3 types of waters. Now, I'm now zooming up with a beautiful photo on the right by Ted, who's done some just fabulous aerial photography in the region. And we're looking down on the confluence with the beautiful blue-green water of the Little Colorado River coming to join the green Colorado River. The Colorado River is flowing from left to right, and this blue water is joining into it. The water on the right at this particular stage, where it's not muddy, is 100% of that is coming out of a spring a ways upstream from this field of view. So that's actually groundwater that's flowing in a river channel. The water on the left is an interloper. It's the water that's coming in from Colorado and points north, high elevation, snowmelt coming down in. So the blue water is the indigenous water rising up in the Grand Canyon region itself, the spring water, and the other water is runoff water coming on by. And where the two come together is kind of highlighted in the left-hand blow up, that we're seeing a visual example of mixing. And it's really beautiful. And some of you have probably had a chance to stand at this point, if you could be there when you're not seeing everything flooded with silt and mud to obscure this effect. You can see beautiful example of mixing. So on the left-hand side, we see it's high salt water in the LCR. In fact, it's carbonated, it's producing travertines. That's like the topic of a whole other talk. But it's beyond your grandfather's hard water, let's say. It's extremely hard water. And so it's got those 2 types of water together. And then the other water is the beautiful drinkable water. Now, when the water is at the surface like this, we say, oh, the water's mixing. And we can imagine that then we're going to see a mixture of the 2 waters as we get below the confluence. So that seems pretty obvious. But what's harder to realize is that in the subsurface, we also have mixing happening as well. And so this map is, go ahead.
So yeah, just to think about the mixing of these waters in the groundwater, and it's very tricky. Water is very tricky stuff. But so here's this region again that we're interested in, and look at all the blue dots those are good drinking water, low TDS water coming off the Kaibab uplift on the north rim. And all the orange dots on the south rim tend to be, not all of them, but tend to be higher TDS, and a lot of them travertine depositing, because those carbonic waters like the Coca can deposit these travertines. So really different waters on the north and the south. And one other point here that's kind of amazed me as we put together this paper we just submitted, Hydrotectonics, is those north rim springs, 80% of the water comes out of 2 or 3 systems. At Tapeats and at Bright Angel Roaring Springs, that's 80% of the north rim water coming into the canyon. On the south rim, it's 90% of the water that gets into the canyon from the regional groundwater is either at Havasu or at Blue Springs. Blue Spring is the biggest source of groundwater coming into Grand Canyon. Both of those are on tribal lands. And so come to the end, we talk about threats and we talk about what's needed for water. We really need a cooperation between different groups about groundwater, tribes, the park, municipalities, etc. So we're going to focus in, take a look at that north-south cross-section line, the red one. And we'll get to that eventually, a north-south line, because that's pretty interesting. But here's here's Blue Springs, huge one coming in here at the Little Colorado. Can you point at that? I don't know. There's a red X there because there's a well, but that's the big one. And then, of course, everyone's familiar with Havasu, the beautiful blue-green waters. 20% of all South Rim discharge from there, but 70% from Blue Spring. It's amazing. Those 2 springs are so important for our geoheritage. And so how does groundwater work anyway? The rain, snow falls on the rim, and it moves its way down through porous materials called aquifers until it hits a confining layer, a shale, something where the water can't penetrate. And so the first one it hits as it comes down is the Hermit Formation. And the area above that we call the sea aquifer. And then if it gets down through the Hermit, it gets into the Redwall Muab aquifer, which is mostly limestone, so caves and karst and fractures and things. And the traditional view is that those were separate aquifers. The sea aquifer, if you live in Flagstaff, you drink from a sea aquifer. And if you go down to Grand Canyon, the RM aquifer provides most of the water for Roaring Springs and Peats and those good drinking water things. But the hydrotectonics, one aspect of that is that those two aquifers need to be thought about as connected aquifers because there's vertical connection between water-bearing units in the upper rocks and the lower rocks. And we'll show you that they have some similarities. Isotopically, that is, in a given place, the sea aquifer is leaking down into the RM aquifer. And then, of course, once it hits the confining layers, the Bright Angel, where all the trilobites are, it migrates out and forms a spring. So here you are at the South Rim, looking up from Havasupai Gardens, the two aquifers, the sea aquifer, named for the Coconino sandstone, but it also includes the Kaibab and the Toroweep. So those upper three units, and then a confining layer, and then the Redwall RM aquifer, and connected by faults. In this case, the Bright Angel Fault offsets the lettering and offsets the rocks. And so we're going to focus on faults as one of the hydrotectonic influences. It provides a motivation. This talk is motivated by trying to get this idea of the tectonic influences by thinking about baselines and the need for cooperation, collaboration to understand Grand Canyon groundwater and springs.
So one of the fabulous things about some of these world-class aquifers in the Grand Canyon region, especially the RM aquifer, but also the Kaibab, is that it has this karst-like behavior, which literally does create, underground rivers. And we see a photo taken by Hannah of a team in there working their way back up through some spring conduits into these massive channels. So we have what we call fast conduit flow. That sounds kind of fancy, but just look at what's happening. These people are literally able to move their way through some of these passages. So both cavers and people who like Huntoon, who sort of followed the water back into the rock and in the RM aquifer, and Rampart Cave member especially, have noticed this and talked about this for a long time. But from a larger scale regional view, it really has not been factored that well into account. So we got to kind of remind ourselves about these things which exist and which are not anomalies. I kind of think of the traffic example. If you look at a map and you were to ignore the interstates, that's what these things are. These are the interstates of water travel in the subsurface of the Colorado Plateau, not just in Grand Canyon, but the Colorado Plateau region in general. And here's a kind of a picture of Huntoon showing, there's spectacular ones, and we love it when we can kind of climb back into a passage and see that. But he's got his fingers in that central picture poked into what he thinks are probably the sort of bread and butter type of passages, which are smaller than you could fit a paddle raft into. Nevertheless, those are still very large apertures for groundwater movement compared to what you can do in the intergranular pore space of, for example, the Coconino sandstone. So the RM aquifer permeability is really dictated by faults and fractures and joints and karst, which links together the sedimentology of the unit and its geologic history, because karst is a part of a history of what happens to a rock after it's deposited, a limestone in particular, but also the structural geology, which controls the fracture and joint patterns and also the faults. The other thing about the faults that you might not think of, you think of them as cracks, but faults can be seals as well as leaky points. And for that reason, it's very important to know what the present state of stress is and what the fracture and fault patterns are, because we can have extension, which allows them to open, which makes them good conduits. We can also have compression, geologic compression, which then prevents movement. So that's the sort of the hydrotectonic ideas linking these different concepts.
Okay, so I think you're getting your head around, there's three kinds of waters. That's a simplification, but the water mixes in the groundwater system, and there's different kinds of pathways, faster and slower. And so we have a mixture of, they're called dual permeability or multi-permeability aquifers. Water moves through at different times through different kinds of conduits. And so on the left here is Roaring Springs that gets all the water to the South Rim Village. And we've called this the water corridor just because it's kind of like the hiking corridor, right? The water comes out at Roaring Springs. If you can point it out, there's an RS up there on the map on the North Rim. And then it's piped to Indian Gardens, Havasupai Gardens. And then it gets pumped up to the village and used and flushed. And I want to talk about that pipeline system and think about the water, that water which we've been piping to South Rim for 60 years. And here's a kind of a blow up. 3 kinds of water again, comes out of Roaring Springs, that beautiful spring, piped over to Havasupai Gardens up to the village, so that where one is there on the South Rim are the big tanks, the water tanks. And when they get low, we have to conserve water up there, etc. Number 2 represents the groundwater system in below Tusayn and Valley and Pinyon Plain Mine, coming back to the threats. All of the number 1 waters at the village get used by tourists and flushed through toilets and processed at the water treatment plant, water reclamation plant. So that's water number 4, gets dumped in along the Bright Angel Fault. And where do you think it goes? You can go there. It's fun to walk there and see it being dumped into this wash. And it looks like that. There's our North Rim water coming to the South Rim, being processed, used and processed, goes down into the fault, disappears. And our hypothesis that we're presenting here is that piping of water for the last 60 years or so, from North Rim to the South Rim, its use and infiltration down the fault has influenced not only Havasupai Gardens, these are waters number 3, but Pipe Creek and essentially all of the springs on the South Rim and Tusayn groundwater, maybe out to Pinyon Plain Mine and to Tusayn. So that's what we're going to present here, this idea of an anthropogenic experiment that I don't think the park was aware of, although they did it for the last 60 years. So here's what the pipeline looks like. North Rim's up there. You can see Roaring Springs. You can see the pipeline, which brings it down past Phantom Ranch. This is oversimplified. It goes by gravity flow, at least it used to, and now they're changing that, much against our recommendation. But it gets to Havasupai Gardens. It's pumped up here to these water tanks, tank farm, used by all the hotels, put through the water reclamation plant, dumped down the fault, come back down, and we think it's influencing and sustaining the springs at Indian Gardens, Havasupai Gardens. So this pipeline experiment lasts 60 years. And you can see the bottom's kind of fun because you see the elevations. There it comes out at 5,200 feet. And it goes up to Indian Gardens by Havasupai Gardens by gravity flow, pumped up the last way. In the old days, they used to pipe it out to Desert View. And of course, now they truck it to Desert View and to Tusayn and to Hermit's Rest. And so this North Rim water is being used at South Rim and recharging the aquifer, is our claim. And we're going to have geochemistry to support this. But if you get Google Earth and you look to the north, from the north to the south, you can see how that water reclamation plant's perched right on the Bright Angel Fault, right above Havasupai Gardens spring. So the idea is, can we show that there's an influence? So let's see. Oh, one other thing, the North Rim water, the North Rim surface water in the upper left, because of the dip of the Kaibab uplift, is running into the canyon, and so is the groundwater. So this part of the aquifer, the RM aquifer, is kind of being drained, and so all the springs are in the Muav. Over here, the surface water is still running to the south, but the groundwater has a bit of a divide here below Tusayn, and the water is flowing both to the south into the canyon and to the north over a kind of a mound. Flowing to the left and the right into the canyon and away from the canyon from a mound in the RM aquifer below Tusayn, and that needs better resolution, but that's our present view of surface water and groundwater, which are the same direction on the north, but in the south, they're different. And notice our little blue triangle of water coming down from the water reclamation plant along the Bright Angel Fault and recharging the aquifer and affecting Havasupai Gardens and Tusayn water. So here's some of the evidence.
So we've looked at our, bottles. Lower left is fresh water, and the upper right has both the electrolyte-rich solution and the carbonated fluids. And these little puzzle pieces are a graphical way of representing complicated tables of water chemistry. So let's just look at the one in the middle at the top, elves, just as an example. They're all done at the same shape, where the common cations, some of these are the softeners in water, but sodium, potassium, calcium, magnesium. On the right-hand side are the negatively charged solutes that are in the water, chloride, bicarbonate, and sulfate. So you have to have your positives and negatives balanced. So the area under the left side of any of these puzzle pieces has to be balanced by the ions on the right-hand side. And then the shape is characteristic of which ions are kind of dominating the water. I'm going to go down to the lower left and let's look at the interloper, the Colorado River, coming from the high Rockies and finding its way down through into the Grand Canyon region, and it has this characteristic shape. And these are milliequivalents per liter of charge. They're a measure of what the total solutes are. And these skinny ones, these three in the left-hand corner, these are all potable waters. Their total dissolved solids is low enough that they're terrific waters to drink. But the Colorado River itself has a different shape characteristically than Deer Dutton and Tapeats, which is like Roaring Springs, looks identical to these shapes. And the bulge here, the mid-waist bulge, which some of us are a little too familiar with, is reflective of a calcium bicarbonate water, which is what happens when you take fresh water and you let it run through a limestone natural plumbing system. And so you get a water of this shape. And so that's very characteristic of the North Rim water that resides, comes on in and interacts with the limestone aquifer. And then these other shapes, Fence Spring, which is, we'll show a little bit more detail on this one. This one is much, much higher in terms of its TDS and way higher in terms of its carbonic nature. So this is a very fizzy water, as is Elves with a very high carbonate content. But we can start to put some different springs kind of in the same families from a geochemical point of view. So the Lava Warm Spring, Beecher, and Elves, these are all springs kind of in the central Grand Canyon region. And then as we move to the right, we're getting more toward western Grand Canyon with the LCR, also with much higher sodium and chloride. So that's a very, very salty water. We had to change the scale here. This is 4 times as wide. And then Pumpkin is here, this number is 150 out here on the side. So if we put the drinkable water from Tapeats on this same scale, it would just look like a vertical line. And they're very top heavy when they have the sodium chloride from the saline units that they encounter in their travels. So different spring groups are stained by the rocks that they move through, and that becomes a fingerprint that tells us about the flow paths.
Yeah, so it's amazing, isn't it? But here's Havasupai Gardens, the red dots, and go up just down and to the right, and you see that the shape of that water is almost identical to the shape of Roaring Springs. So this blue dot is very similar to the shape of these springs beneath the recharge area, we're saying, beneath the infiltration area. So it's a solute evidence that they might be influenced. But we have better evidence than that. But it requires a little explanation of stable isotopes.
And this is such a powerful geochemical tracer of water. It's very important to understanding climate change as well. So it's worth just kind of thinking about how we use these different isotopes of
hydrogen and of oxygen, which compose the water molecule H2O. And in the upper right, just kind of showing you the possible isotopes that could be in any given water molecule. We have one oxygen, that's the big bad boy here, the negative ion, and then the positive H plus is there's two hydrogens for every oxygen. And the oxygen can be either an 18, being the mass number for that, or an O16. So we have, this would be light oxygen because it only weighs 16 mass units, whereas this is 18. And so that's, 18 to 16, it's a fair amount heavier. When we look at the hydrogen, it's either hydrogen or deuterium. That's a 50% increase in mass from hydrogen perspective. And we can either have HH O16, or we could have deuterium O18. That would be the heaviest a water molecule can get. And so we have this huge mixture. In the real world, by far, the dominant is to have hydrogen on both and to have, the lighter oxygen molecule. But so that's the most common oxygen molecule. But we have instruments, mass spectrometers, that can measure it down to a part. We call it a part per mil. A per mil unit is a part per thousand in isotope speak. So the mil isn't short for million, it's for mil, which means thousand. And so these are part per thousand differences that we're measuring in how heavy the water molecule is. So now for a second, just go over to the cartoon in the lower left and just think about what processes that happen in the water cycle and how those might affect the isotopes of the water masses. So our standard water is what we think of on our blue planet. That is the world's ocean. So standard mean ocean water is our reference point. That's 0. Okay, that's what we're going to measure deviations from. So that's why we call it SMO, that's standard mean ocean water. And what happens when we evaporate is that we evaporate the lightest. That would be if we had an O16 instead of an 18, and if we had hydrogens instead of deuteriums, we're going to preferentially evaporate the lighter mass molecules. Now, as that air mass then moves over land, we're going to be working the problem from the other point of view. We're going to take vapor, which has already been lightened relative to standard mean ocean water, and we're going to start condensing it. And we're going to rain out something that's heavier than the cloud, and we get it lighter and lighter and lighter as we go further and further from the ocean, and we rain out the heaviest bits of that light air mass. So that's kind of the cartoon idea, and it's very simplistic. One of the things that happens is if we have high temperatures, we don't get as good of a fractionation because all the molecules are excited when they're hot, the kinetic energy is high, and it can't tell the difference between the different masses of the water. So we don't get very much fractionation when we're warm, but we get a lot of fractionation when it's cold. So this cartoon on the right, this is a graph where we plot the difference in the hydrogen isotope composition relative to standard mean ocean water. And we measure that compared to the oxygen, and we get more fractionation of this because it's a 50% difference between D and H, so the scale moves faster. But the relationship of evaporating water and condensing water leads to this incredible line here called the meteoric water line. One of the most fundamental observations about water and its isotopic behavior is that it behaves very closely to this line, reflecting just condensation and evaporation of the air and the water. Now, what happens as we zoom into a particular place like Grand Canyon, when we're in the winter, we're going to be down and to the left because it's colder and we don't get so much fractionation. Let's just look at where 0, 0 is. I'm tracing the horizontal line 0 up here, and the 0 from the deuterium line over here, that would be the ocean, would be right there. And so the most fractionated we get would be way down and to the left. And then if we have warmer conditions, we're going to be up to the right. If we evaporate, we preferentially drive off at a different slope than the conventional meteoric water line. So those are lines that come out looking like that when we look at data. And the other factor is that when we think about temperature, winter and summer is also a little bit like going up in elevation. That would tend to put us toward the lower left. Lower elevations would put us to the lower right because we have warmer temperatures. So given this sort of really quick introduction to the behavior, we're going to zoom into a very, very tiny space on this graph and look at what happens with Grand Canyon levels.
Okay, so I know you're all saying those dots in the up and right are from the North Rim, and the ones down and left, no, it's the other way around. Down and left is cold in winter, right? That's from the North Rim. And up and right is South Rim waters. And they're different fingerprints, we call it. South Rim, North Rim. And so, and yeah, well, there's the Colorado River, and
they're coming from high elevation, way down off this graph,
down off there,
because the Rockies are much higher.
So if we think about the rain and snow that falls on the peaks or on the Kaibab uplift, it's kind of surprising. We would expect that the peaks would have all this down and to the left stuff, and it does, but it mixes with all the summer rains and stuff across the Coconino Plateau, so that the Kaibab uplift is the one that's giving this best fresh water coming down from the North Rim, all the blue dots on the map earlier. And the South Rim water, groundwater, does have that great stuff from the sea aquifer beneath Flagstaff, but it's mixing with the Coconino Plateau lower elevation waters. And where do you think Havasupai Gardens plots? That's the red oval there, right in between, right at the junction between North Rim and South Rim water. And our hypothesis is, well, that makes sense because the North Rim water is being piped to the North Rim, to the South Rim, used and flushed, and mixes with South Rim water. So we get an isotopic mix, and we can actually quantify it and use means and all this kind of stuff. But this is a mixing model between Roaring Springs down on the left, the blue dot, that's the base flow, and the valley groundwater wells up and right, and all these South Rim springs like Havasupai Gardens and Pipe Creek and Horn Creek, and all these ones are in between and represent a mixture of waters with different fingerprints. And here's our estimate of the mixtures. Water reclamation plant there's in blue, dumping the water down the fault. Havasupai Gardens, probably about 40% of that water is sustained. Is the way I think this is a good thing, that we're taking North Rim water and we're sustaining all these springs with water from the North Rim. And so it's a good use of, we use it twice.
And you should mention, it's not only the water reclamation plant, it's also rejected water. There's pipeline water that's rejected at Havasupai Gardens. And then secondly, there's also a lot of pipeline leakage, and there was a lot more pipeline leakage in the past than there is today.
But then the arrow at the bottom down the Pinyon Plain mine, that's just one of these uranium mines. We think there's 20 to 40% of that mine water is coming from the North Rim. And that's a dramatic thought because of this groundwater bulge beneath Tusayn. So everything's connected in our view beneath these different places, and we got to talk to each other about the groundwater.
So believe it or not, we're kind of wrapping up some of this, flow history. And this is just one of the most fabulous experiments, which is still getting picked up and continued literally this year with the great snowmelt that we had. And so there's a tracer that was purposefully put into this beautiful recharge system on the North Rim on the Kaibab uplift. And in the upper right, we're looking at some of the original presentation of this work was by Casey Jones, who was working for the park with Abe Springer's group, and Ben Tobin when he was park hydrologist. You can see the blue line of the Colorado River winding your way across. So we're kind of zoomed in to the Kaibab uplift area. And these circular features represent the points where the water was injected. I should have put a picture of Ben here pouring that dye into the snow, into the sinkholes, which were identified as major points of recharge on the uplift. And so they put them in here, and it's kind of like, when you try to hit the broadside of a barn and you kind of miss it. So they started in, up a little higher on the uplift, and they were trying to hit to where they would get a tracer at Roaring Springs. And it took a few tries to chase it with snow at the right time of year to get that to happen. But, and we can talk more about what these represent. The bottom line is you're pouring in a dye that will persist in the subsurface for a while, but it will break down. It's a harmless kind of a dye in terms of the groundwater ecosystems. And then the triangles represent receptors. And in this publication, they highlighted the receptors which received hits from the dye. So that is a literal connection that had to be, this is an anthropogenic tracer. It's not something that's out there by accident. So it's really awesome that they were able to connect this up. What was super surprising, of course, is that they poured it in here on the Kaibab uplift, trying to hit Roaring Springs, and they hit over here at Fence Fault, 30 kilometers east, and they hit way down almost to Stone Creek, to the west. And so this water was moving over literally 1 to 2 seasons, 40 kilometers in each direction, perpendicular to the direction that they were trying to reach, straight down the uplift to Roaring Springs. So, unexpected results, but not when you consider this interaction of stratigraphy and faults. So, so now I'm going to take you to a much more, complicated looking diagram, but instead of putting arrows sort of just across space here, we're really focusing on the mapped faults, and the light white lines represent the different elevations of the aquifer boundaries. And
and these basins, we won't get into it too much, but we think of these as sub basins that are separate, probably geologically and hydrologically, and there they are, these big springs coming out of.
Mention the names of the basins.
Well, there's Havasupai Basin, Fence Basin, right on the Navajo, and then Blue Spring has both the Navajo and Hopi things. So just to mention a couple of fun things. On the Fence Fault, there's 2 springs on either side. It's really cool. And here's one on the east side, and here's one on the west side. They have the same water isotopically and geochemically, and we've been monitoring these for about 10 years to see what they're doing, because this is part of what's happening to this groundwater over 10-year time. And isotopic data show they're the same on either side, disconnected from the river. It's a very neat system. And Vasey's, which is just downriver from Fence system, is a different water. It's coming from the Kaibab uplift. It's affected more by these fast pathways. And so 2 very nearby springs. And one of the evidences that Vasey's is so, affected by these fast traveled waters. It got hit by these dyes 3 times, and we've all floated down there. If you have, sometimes it's roaring like on the left there, and sometimes it's nearly dry. So there's a big component of the fast traveled water in this karst baseflow. And so there's lots of different waters, lots of different histories. And that's sort of the main point. Here's the Fence fast pathways coming down from the Kaibab uplift, slow pathways in the karst baseflow. They get it under the river in some kind of a confined fault system. And so we can study what the baseflow is doing, and then we go to a place like Vasey's, and we can study the effects of fast traveled pathways to try and understand this complex mixing of water types and water pathways. And we won't belabor this, but here's 10 years of monitoring of the base flow. And we put these probes in, and we correct for the barometric pressure, and we measure the pressure and the temperature and the conductance. But the only thing I want to emphasize is Fence East has decreased in temperature by 1 degree C in 10 years. Fence West, 1 degree C in 10 years. They have the same water. And so why is it that the base flow is getting cooler over 10 years? Our hypothesis is there's more fast pathways bringing in fast traveled cool water that's mixing with a base flow which is decreasing. And that's kind of scary.
That's what you mean when you say mining groundwater is eventually having an effect down in those pools, those deep pools, Fence, Havasu, and the LCR.
And in during the same period of time, of course, there's less snowmelt on the rim and less fast traveled water. So the base flow is decreasing in temperature because there's a higher proportion of fast traveled water. At the same time, the amount of fast traveled water is decreasing. It's kind of scary sight, but it's only 10 years of monitoring, and we need to do it for another longer period of time to see if this is evidence that the base flow is decreasing all over the Colorado Plateau region, but that's our hypothesis. And this is super fun. I think this is really near our last slide. When I was at NAU as an undergrad, Dave Brumbaugh started a seismic network, and all these red dots represent epicenters for earthquakes, small ones, magnitude 1s and 2s and 3s up to about 5 or 6. And I couldn't figure out why we'd have a swarm of earthquakes at the South Rim Village inside that box. Well, there's other swarms. There's one at the San Francisco Volcanic Field. That makes sense to me. And along the Hurricane Fault and the West Kaibab Fault. But why is that swarm there on the South Rim? So if we blow up that box in B in the lower left, there's just a whole bunch of earthquakes happening on these faults, northwest and northeast and north-south trending faults. And our hypothesis is that the injection of the water at the water treatment plant in the South Rim Village that's allowing these faults to slip. And they're already under extension. These beach balls on the right side are telling the seismologists that these faults are under extension. So the lower graph here's the historic earthquakes. This is the confluence of geoheritage and human heritage. Is the amount of water we've pumped into the ground is that blue line, millions of liters over 60 years. And the amount of earthquakes is increased. And we think we're causing the microseismicity by this injection. And that's a good thing too. I'm kind of looking at the rosy side of things. This injection of fluids is relieving the stress on faults so that we won't have big earthquakes, we have a lot of little ones. So this hydrologic pipeline experiment, I don't think is a serious negative thing for either the seismicity or the water. And just to mention the uranium again, coming full circle to the new monument, Pinyon Plain mine there, F is one of the higher places for uranium. Pigeon Mine to the north, and D. These are places that are in this new national monument, but they're excluded from, they can still mine, I think. But these uranium-bearing breccia pipes are also vertical conduits between the sea aquifer and the RM aquifer that help make this groundwater system so complex. And of course, the water from Pinyon Plain Mine, we think, is being affected by this North Rim recharge. And of course, it may be making its way to Havasupai Springs, which is down gradient. So the Havasu Spring, huge amount of water, is, I think, at risk from this uranium mining at Pinyon Plain. Orphan Mine has been abandoned as a mine, but of course, it's still leaking uranium into Horn Spring and stuff. So this idea of threats and how we look for sustainability of our groundwater system is all connected to this complex hydrotectonics, we're going to call it, of the region's groundwater.
And I know that was a super race through some pretty complicated ideas, and folks here are very familiar with locations and maybe with the anthropogenic concerns, maybe with just the general geology and hydrology. So we want to leave some time for questions.
Wow, that's pretty amazing. And yeah, I'm gonna take off with some questions here, and then we'll open it up to the entire group. Just a couple questions. I'm trying to wrap my head around a can of Coke and my drinking water bottle. And I'm thinking about old water and new water, North Rim and South Rim. Because the lay of the land makes this tip high on the North Rim, lower on the South Rim, heading down toward the Verde and Phoenix. The carbonates, is that the fresher water coming out of Tapeats and Bright Angel, is that because that water's a lot younger? And the south side water that we see is actually coming from the south and is a lot older?
That's the pathway part of it. And then the origin part of it is, we didn't mention the CO2 much, that's Lori's favorite thing, but the CO2 is, a lot of it's coming from magmatic sources. So the San Francisco peaks has CO2. Well, basalts have erupted as recently as 1,000 years ago, but the CO2 is still making its way to the surface, the volatiles from deep magmatic sources, both below the peaks and the Uinkaret volcanic fields, the young volcanic fields. So the different types of water, the CO2 is coming from San Francisco peaks, basically. And that's why the South Rim waters are more carbonic.
And the Uinkarets.
And the Uinkarets. But the pathways are also important, old and young.
The only thing that makes me scratch my head is I'm thinking about Blue Springs, and I'm thinking about the huge LCR aquifer, really big. And I'm like, wow, I would just expect that water to be a lot, I want to say kind of fresher, a lot more North Rim like, because of the size of the basin.
Yeah.
But clearly that's not the case. Do you have any thoughts on that?
Yeah, you know, one of the things that we need to build is, you know, when you go up to the Powell Center up there at up north and look at that big giant map, you know, in Page, you know, it's just so fantastic to like physically see that. And if you go to, you know, other places, they'll show you the subsurface in a big kind of a diorama kind of way. And you need to kind of see these systems, you know, because your intuition is exactly right. And those three big basins that Karl was showing, you know, the place is not a layer cake. It looks like a layer cake in so many ways that you get lulled into thinking of it. But the average elevation of the RM aquifer, and think of it as the top of the Bright Angel, is sitting at a spot where you almost have to think of like, I don't want to say stagnant, because, you know, on geologic timescale, nothing is stagnant. But you got these pools, these big reservoirs where the water has what we call a much longer residence time. That lets the salts build. There's a lot of other things that happen in water. It ages, you know, groundwater age. And so the LCR area, that fence area, and the Havasu Basin area are these pools, and they're warmer. They've come to the geologic temperature at depth in the earth, so they're warmer, they're saltier, and then they have the CO2 is fizzing up into them. That's almost like another story happening underneath, but they've accumulated that CO2 and a little bit of stuff coming with the CO2 that's very special. And so it's a complicated story, but that water coming out of the LCR is from one of these big reservoirs.
It's San Francisco Peaks water. It ought to be fresh, but it's had a long time in the aquifer, residence time, and it's got the CO2 from the magmatic sources that are underneath the peaks. So that water, huge volume, but it's got a lot of things being dumped into it.
Fascinating. So even though it happens to be in the Little Colorado River in a giant drainage, it has nothing to do with eastern Arizona, far western New Mexico, with a whole watershed of the LCR, in a way.
The Navajo hydrologic basin to the east contributes a little bit to the LCR system, but that's mostly from the San Francisco Peaks. That way. Wow,
fascinating. Okay, and then one other question. I was thinking about the I think it's the Pinyon Plain mine, the uranium mine. Pretty near Red Butte, where the president signed the proclamation today. I can imagine that breccia pipe is going all the way down to the level of the Colorado River. How does the North Rim water show up over there? Or is that Colorado River water that shows up over there? That makes sense to me, because the Colorado River, you know, all the North Rim water is going to bubble out in the big springs. The river's below that. So could that be river water that's showing up over there?
The Colorado River can't get in because there's other water there already.
The aquifers are pouring out into the canyon.
Yeah.
So the Colorado River is just kind of passing on by.
Got it.
But the idea we have is that this bulge in the groundwater near Tusayn allows water to migrate from the South Rim. Remember, the groundwater, surface water is flowing south, but the groundwater is flowing both ways.
Okay.
And so groundwater's flowing from below the South Rim towards, there's higher percentage of it at Tusayn, still some at Pinyon Plain Mine, and maybe Summit Valley. This needs more work. But
so the groundwater mound was not identified by us because we're working with natural springs, whereas, you know, Bill's and others from the the water, group in Flagstaff and the USGS more broadly identified this bulge, at least, in a crude way, because there's just so little well density that it's really hard to, to document that. You need more density of groundwater measurements. So they hypothesized that, and we haven't mentioned pumping, but of course, the idea of pumping, increased pumping, it's going to do things like shift, a groundwater divide, which itself is partly dictated by structural geology. So, a hydrologist, ideally, we always have kind of these jokes about, what they really like is a sandbox and everything's simple. And you couldn't get further from that kind of a condition, and then add, a world class karst aquifer, which karst hydrology is already complicated because, you can have disconnected things, water levels here and here. Cavers know all about this, sumps and really complex behavior. So that means you can have water aging in different places, and you can have a really wet year that sweeps through and kind of pushes out with the old and in with the new, and then it sits there maybe for 2 El Nino cycles until you get another big push. So it's really complicated, even on the young end, where we use dating things like tritium and C14, that date the very younger parts of the water cycle. And even that is really complicated in karst settings where you have areas where you can have some perching. We're not saying perching doesn't happen, but if you're worried about a threat, you don't want to make the best assumptions. You want to say, we can't reject the idea that this stuff is going to behave just exactly like those other tracers and go 30, 40 kilometers. And you just put a circle around that and around every one of these, places where people are saying, no, it's going to be fine. And we just are not, kind of going with that. I think you can present the concept that says, well, hey, we're not saying it's 100% that it is the mining activity that does that, but we certainly can't reject the idea that the mining activity has done it. You can say the numbers show the same things. Okay, we look at 600 water analyses over 30 years, and only 11 of them exceed things. And they all happen to be within, a couple kilometers of active mining, but that doesn't prove it. Yeah, but it doesn't rule it out.
Exactly.
Let's go on the threat side. Let's be conservative and protect the water, because I know from New Mexico, we have a huge uranium legacy in New Mexico, different kind of setting. But you can't pull those things back out of groundwater once you do it. It's not like cleaning up an oil slick on a lake.
That's the Tuba City aquifer next to the Superfund site from the uranium mill that was there. Sure, these plumes move, they move slowly, but you can't stop them, and there it is. Kim Christensen had a question which jumps right into this, which is, y'all had some thoughts on gravity feed from Roaring Springs versus pumping from the Bright Angel Delta. Can you expand on that? Because I'm very fascinated about that.
The letters and the public comments should be accessible to the Historical Society. But yeah, we've
you're giving up the energy needed to pump from Phantom Ranch to Havasupai Gardens, and that's considerable. Extra pump. What you're gaining is, instead of one spring, Roaring Spring, you have more springs, Angel Spring, and all of the Bright Angel Creek flow. So you're gaining the park decided, and you're also gaining. You don't have to fix the through the box there on the North Kaibab Trail, where the flash floods wipe that pipeline out regularly. You're gaining a maintenance thing. So it's a cost balance thing. The park just decided the extra water and not maintaining that through the box is worth the pumping. And we kind of disagree.
So the unanticipated things are, we've talked about all kinds of contamination that are just, super bad sounding, right? Uranium, you can have arsenic, you can have, just super high salts and everything. But what the bane is to a freshwater intake system is simply the cloudiness of the water, the turbidity. And try as we might, I've got temperature data going back 12 years, here and there, and this, and Bright Angel Creek's been monitored for fish and for all this other stuff. Nobody has a really good turbidity graph, but everybody, how often is it cloudy? If your
Every
eye
spring.
sees the water, if
Yeah,
your
exactly.
if your eye sees it as cloudy, that's way beyond what a intake plant can take, right? Because that's going to just jam up the works.
Right.
So what do you do with water like that? You have to settle it.
Right.
Okay, how many days, how many turbidity days do we have consecutively? What kind of settling? I just haven't seen those questions addressed to my own satisfaction. I go to, in my mind, to a town like Durango, which is not that dissimilar in terms of the water done. So Durango's got the Animas and they also have the Florida. And when that trigger hits of any turbidity in the Animas River, which happens all the time, and sometimes that's bad water. We've all seen the mustard coming down there, but when that happens, they switch over to the Florida River. Well, what does the Florida have that the Animas doesn't have? It's got Lemon Dam up there. It's got a reservoir. So what's up there? What's up Bright Angel? There's not a place to settle the water.
We're worried about this new decision, but it's water under the bridge, as you might say.
Yeah.
And they haven't burned any bridges completely. The pipeline's still being left in there. We recommended that, and there's good pipeline technology now. They're doing a lot of infrastructure stuff with at the South Rim, water treatment plant, things at Phantom that would be needed anyway. So it's a work in progress, and the people in charge decided on one cost benefit decision, and we'll see how it goes.
I totally understood. But just the tannin in the water in the spring.
Forest fires.
It's not. I don't think the tannin part of it is going to be that as much a problem as like literally mud.
No, but my thought was, here's a highly turbid system, whether it's the spring water, which has the tannin issue in the spring, or as you say, anytime there's a monsoon storm or some sort of even snowmelt event, which is going to increase the turbidity of the water that's going to be at Phantom Ranch at Bright Angel. So it's just fascinating issues with no simple answers, as you point out.
Right.
Well, time will tell. It'll probably all work out fine. Rest easy.
Let me address Steve's question about how old the water is coming out at Roaring Springs.
Okay.
Super good question. It's mixed, but some of it has tritium in it from the 1950s above ground testing of atomic bombs. That tritium spike is recognizable in some of the water that's coming out of Roaring Springs, and so are these dye tracers. So some of that water is months old, years old, some of it's decades old, and some of it's older. And how old the oldest stuff is that mixes with the youngest stuff, we don't know.
Yeah,
but,
so a groundwater age is always you think that the water is going to have one age, but in fact that water's got water that came from different flow paths, some older, some sat around for a while, and some young. And you can have it very close to each end member, and Roaring Springs is very, very close to a young end member, and you're going to see a storm, visually see that thing flush through.
it's a lot younger than the South Rim water, let's put it that way.
Right.
And Vasey's does the same. People have seen mud, stuff come out from a really super big event historically. There's anecdotes about that. I think it'd be a great project actually to collect photographs, because Vasey's probably gets photographed almost on a daily basis for 60 years. Let's compile those photos. You could do so much with those pictures, because now the park is doing a fabulous job with monitoring in there, and then we can calibrate that to photographs, and then we can use photos to go back into time and mine that citizen science.
And let me address Janine's question about the dangers of uranium and what the levels are. The United States Environmental Protection Agency has standards for what exceedances, are dangerous and potentially dangerous to humans. Can't remember what it is for uranium, but I think it's 30 milligrams per liter.
No part per billion.
I think it's 30 milligrams per liter.
No, it's not milligrams per liter.
Anyway, she's a geochemist, but it's on one of those slides in there about what the exceedances are. And Pigeon Plain Mine, for instance, is not exceeding that danger level. The Pigeon Mine to the north is Pigeon Spring is to the north. So anyway, that's quantifiable. And as Lori says, we're just erring on our recommendations. We err on the side of being conservative about potential future impacts. And right now, I don't think you can point at any of these mines and saying they're jeopardizing anyone's health, but let's be conservative about it.
Yeah, absolutely. I did want to mention Dick Brown, past president of the Historical Society, had a little post here that says, "Wow, Laura and Karl, fantastic presentation, great research and analysis. Thanks for helping us better understand canyon water. Dick Brown, University of New Mexico, class of 1972.
That's
About that.
fantastic.
Y'all, you've been asked to unmute. If any of the audience has any questions, I'd throw it open and go for it.
I've got one.
Yes, please.
Yes, wonderful talk, very detailed. A little hard to understand for us non-hydrology people, but the one question I have is you talked a lot about the difference in water and what's in water and what's not in water, but you didn't say a lot about what water was drinkable and what water is not drinkable and what needed to be done to water to make it drinkable. And the reason why I ask that is because our water that we drink in Oak Creek Canyon comes out of a spring in Oak Creek Canyon, which creates all the water for Oak Creek. And we've been drinking it for 80 years. None of us have died yet. But I wonder if you could say a few words about what water is drinkable, what water is not drinkable, and what has to be done to the water to make it drinkable if it's not drinkable.
Well, that's, the guidelines, hey, government regulation, right? To make water. So the regulations apply quite differently to what might happen in, say, a well of a small area, a personal well, versus when you're doing municipal water supply. You fall under a different envelope of what you're required to meet. Now, generally, surface waters are exposed to agriculture, to runoff, to somebody changing their oil, all this kind of stuff. So surface waters generally have a lot more treatment that's involved to be sure you're getting away from that, whereas groundwater in a way is itself protected, from all of that sort of thing, but it has its own natural things that could be contaminants. Now, back in the day, maybe, Paul, I don't think you're that old, but, Glenwood Springs, people would go to a tuxedo dressed waiter to take the waters at Glenwood Springs and drink the lithium and drink the uranium. They thought that was a very healthful thing. And we need to distinguish between what we would call taking a tonic versus your daily water that you drink and that your children drink and that nursing mothers drink, which is a big difference between taking something like an emetic, something like sulfate-rich water, which would maybe make you vomit or you'd lose weight if you drank it for a while, but it's not going to kill you over a short term. But if it's your water for your whole life, then things like low amounts of lead, low amounts of arsenic, low amounts of uranium. The uranium is not dangerous because of the radiation of the uranium. It's a heavy metal and it does other things, in your system. And those things build up and your body has places to sequester those things. And then you reach your limit. And that's kind of the problem. Or eating fish that are living in that water, So different waters have different problems. And, generally, if it's a municipal water supply, they're required to do, regular analyses. And then depending on what comes up in the analyses, if they see some of those little red lights going off, well, here's a treatment thing that you're now required to put in place for that water. And so that's how the treatment recommendation comes up for different waters, is based on that profile of what the natural contaminants are, which differ from region to region. But Roaring Springs, water just doesn't get better than that.
Well,
really.
Oak Creek is like Roaring
yeah.
Springs and North Rim water. It's low TDS, comes from high elevation, and so it's one of the best waters around. Doesn't mean it can't be contaminated, but that's a good upper world water, we call it.
Mm-hmm. Thank you.
Nice. Anyone else? Any more questions this evening?
Yeah. Did you answer that one?
I've got one question, if we can change the subject.
Of course.
What did the president do today?
Today, well, Laura and Karl.
I had a slide I could go back to, but he flew to Arizona, and then he went up up to the monument area.
To the Red
and
Butte Airport,
At where?
the Red Butte Airport,
The Red Butte Airport. Okay,
north
so
side of Red Butte.
they jumped up there.
The old
Yeah.
airport?
Yeah, the old airport.
He obviously didn't go in an Air Force One. Was he with a helicopter?
I wasn't
Probably.
there. The White House did a live cast of the event, so I'm assuming that they came in by helicopter, or they could have driven over there from the Tusayn airport, which would make a little more sense.
Well, can Air Force One land at the Tusayn airport?
Oh, yes.
I don't.
Okay.
Yeah, they flew in vehicles that they drove.
Okay, Christy says they drove, so somebody was watching, and maybe somebody was even there, which is awesome. So there's there's been a declaration of reserving these areas from any additional mining claims and so forth. But there's a lot of claims that have already been made that are grandfathered in. The other aspects, I just encourage you to read about it, the details of it, because of course it's also parts of it are going to be managed with tribal units, and maybe we've got somebody here as a park representative also, but it's being
But
co-managed.
in general, what area is it? Are they talking about it being North Rim and South Rim?
There's
Yeah.
three different areas.
Can I go back to my my picture real quick? I'll just share the map, which was from the
You bet.
let's see, I gotta first stop the show and then I know it's always different when you're on
So
Zoom.
Paul, the area includes on the south rim, the Tusayn Forest District, and on the north rim, House Rock Valley. There it is, the map on the right here. Thank you.
And there, in this.
So Kaibab National
this-
Forest in the south,
Okay.
House Rock Valley north of the Arizona State Fish and Game land where the bison are, and then
Okay.
sandwiched between Grand Canyon Parshant and the Kaibab National Forest, BLM land in there.
Okay. So was any of it reservation?
No, well, it's traditional use land.
Right, but it's not part of the Navajo or the Supai or the Havasupai reservation.
That's right.
No, yeah.
So it's basically government land, Forest Service land or
And BLM, yeah.
BLM. Okay.
That's right.
And I'm sure we'll all be hearing more about that.
Yeah.
But that's yeah, a lot of people have been working toward that, and I'm sure there's people that are finding, flaws with it.
I was talking with Jeff Ingram this afternoon about it. Ingram, of course, worked with Senator Goldwater and many, many others on the Grand Canyon Enlargement Act of 1975. And the heart of that act encouraged the National Park Service to work with all of its neighbors to recognize the greater Grand Canyon region. And so Ingram is thrilled to see almost 50 years after the 1975 Act, to see slowly and steadily the areas surrounding the Grand Canyon to become incorporated into this Grand Canyon homeland. So really, really just a wonderful day.
Yeah, and I mean, from a groundwater point of view, you've really got to protect that broad area. Because
Yes,
Grand Canyon is kind of like the sump where, it all moves toward there. And, if Larry Stevens were here, he would be talking about the ecosystems and the endemic species and the keystone aspect that these places serve. And, just like Vasey, turn off the faucet. Well, these deep pools of fence and the LCR and the other, our long-term monitoring showing we're seeing a very tiny temperature change, but this is over like 5 years. And Barton Spring, one of the world's largest karst springs down in Texas, they monitored that thing for over 15 years before they started to discern an El Nino, La Nina kind of effect in their groundwater system, because it is a big reservoir, if you want to think of it, but it doesn't mean it's immune, just like Lake Powell. Who'd think that we'd be at Deadpool,
that's right.
So,
Yeah. Helen Fairley just put up a really nice note. The proclamation specifically calls out the entire watershed and springs as some of the critical resources to be protected by the new monument. That's lovely.
That's awesome.
Yep.
Yeah. Well, I
Well-
think it's getting close to 7:30 here. Local time. We are going to wrap up this wonderful virtual outing. I'd like to thank Laura Crossey and Karl Karlstrom for this incredible presentation this evening. I'd like to remind everyone that a month from now, that's Tuesday, the 12th of September, same time, 6 o'clock Arizona time, Jerry Snow is going to be talking about Navajo code talkers. I hope to see you all there then. I hope you have a wonderful month as we sign off, and we'll hope to see you in September. Have a
All
great
right,
evening.
thanks for coming, folks.
Good night, everyone.